In December 1968, somewhere in the Nevada desert, engineers fired up an engine that would change everything. But when they shut it down, the entire test stand had become so radioactive that they had to control robots from bunkers just to examine it. This was NERVA, the nuclear engine for rocket vehicle application, and it worked. The technology was real, the tests were successful, and according to the plans on the drawing boards, it would put humans on Mars before the end of the century. But there was a problem that no amount of engineering could solve. Every single launch would release radioactive material into Earth's atmosphere. The scientists building it knew it, the politicians funding it knew it. And yet, for more than a decade, the program continued. This is the story of how America's brightest minds, seduced by the promise of nuclear propulsion, built a rocket engine that could have transformed humanity into an interplanetary species. And the moment when we collectively decided that some prices are too high to pay, even for Mars. To understand why NERVA was so revolutionary, you need to understand the fundamental problem with getting to space. Chemical rockets are pathetically inefficient. They work by essentially lighting controlled explosions beneath you and riding the blast, burning through enormous quantities of fuel for relatively modest velocity gains. It's like trying to cross an ocean by throwing rocks backward from your boat. Technically it works, but you're going to need a lot of rocks. For decades, this inefficiency was simply accepted as the price of spaceflight. Then, in 1955, something changed. Scientists realized that if you could heat propellant using a nuclear reactor instead of chemical combustion, you could achieve performance that made conventional rockets look like antiques. The concept was elegantly simple. Use a nuclear reactor to heat hydrogen to extreme temperatures, then expel it through a nozzle for thrust. No combustion required, just pure nuclear heat converted directly into velocity. The promise was intoxicating. While the search for specific performance numbers continues, what we know for certain is that nuclear thermal propulsion represented a quantum leap beyond anything chemical rockets could achieve. The difference wasn't incremental, it was revolutionary. It meant the difference between reaching Mars in months versus years. It meant larger payloads, longer missions, and destinations that had previously been pure fantasy. For the engineers working on the problem, nuclear propulsion wasn't just an advantage, it was destiny. In 1960, NASA established the Space Nuclear Propulsion Office with Harold Finger as its first director. Finger was a true believer, convinced that nuclear propulsion was humanity's inevitable future. His challenge was formidable, convincing a skeptical Congress and an anxious public that putting nuclear reactors in space wasn't just safe, but necessary for American supremacy in the Cold War space race. The Soviets had beaten America to orbit with Sputnik in 1957, beaten them to putting a human in space with Gagarin in 1961. The space race wasn't about science. It was about proving which system, capitalism or communism, represented humanity's future. And in that context, nuclear propulsion looked like the ultimate trump card. The program that would become NERVA actually began in 1955 under Project Rover, a joint effort between the Atomic Energy Commission and NASA to develop nuclear thermal rocket engines. Between 1959 and 1962, researchers conducted multiple reactor tests, gradually pushing the boundaries of what was possible. These weren't paper studies or theoretical exercises. They were building real hardware, running real tests, generating real data. The Kiwi A test in 1959 ran for 5 minutes at 70 megawatts of power. Each subsequent test pushed further, ran hotter, lasted longer. The technology was maturing rapidly, but NERVA wasn't the only nuclear propulsion dream being pursued in those heady days of the early space age. Across the country, an even more audacious project was underway, one that made NERVA look conservative by comparison. It was called Project Orion, and its concept was breathtaking in its simplicity and terrifying in its implications. Instead of using a nuclear reactor to heat propellant, Orion would detonate actual nuclear bombs behind a spacecraft and ride the shockwaves. Small nuclear explosives would be ejected from the rear of the vehicle, detonated at a precise distance, and the blast would strike a massive shock-absorbing plate, propelling the spacecraft forward. Then another bomb, and another, each pulse equivalent to multiple Hiroshima bombs. Hundreds of detonations just to reach orbit, thousands for an interstellar journey. The physics actually worked. The engineering team, led by physicist Freeman Dyson among others, calculated that an Orion spacecraft could reach Alpha Centauri within a human lifetime. They even built a small-scale test vehicle and flew it using conventional explosives, proving the concept wasn't just theoretical madness. The spacecraft would be built around the pusher plate, a massive shock-absorbing surface designed to withstand repeated nuclear detonations. The plate would be coated with graphite grease that would ablate with each blast, carrying away heat and protecting the structure. Behind it, enormous shock absorbers would compress and expand, converting the violence of nuclear explosions into smooth acceleration. It was engineering at its most audacious, turning the most destructive force humanity had ever created into a means of transportation. But the terrible realization was unavoidable. Orion would require hundreds of nuclear detonations in Earth's atmosphere just to reach orbit. Each detonation would release radioactive fallout. The cumulative effect would be catastrophic, and when the Partial Test Ban Treaty was signed in 1963, prohibiting nuclear explosions in the atmosphere, underwater, and in space, Project Orion's fate was sealed. You couldn't launch it without violating international law and poisoning the planet. The project was quietly discontinued, a victim of its own ambition. NERVA, by comparison, seemed almost responsible. It wouldn't require atmospheric nuclear detonations. The reactor would only reach full power in the vacuum of space. It could theoretically launch from orbit, assembled by conventional rockets, then ignite safely above the atmosphere. It was nuclear propulsion with a human face, ambitious but not insane. And so, while Orion died, NERVA lived on, attracting funding, political support, and the dreams of visionaries who saw it as humanity's ticket to the solar system. No one championed NERVA more enthusiastically than Wernher von Braun, the German rocket engineer who had designed the V-2 for Nazi Germany, and then became the architect of America's space program. Von Braun was a showman, a salesman, a man who could make Congress believe in the impossible. And in 1969, fresh from the triumph of Apollo 11's moon landing, he unveiled his vision for Mars. It was spectacular. A fleet of NERVA-powered spacecraft would launch from Earth orbit, their nuclear engines glowing as they accelerated toward the red planet. The journey would take just months, not the years required by chemical propulsion. Crew compartments would be spacious, with room for laboratories, living quarters, everything needed for the long voyage. They would arrive at Mars, establish a base, conduct exploration, then return home as heroes. Von Braun had the timeline mapped out. With continued funding, humans could walk on Mars by 1982. The technical foundation was solid. By 1968, NERVA engines had completed over 17 tests. They had run for cumulative hours at temperatures that would melt steel. The program had demonstrated that nuclear thermal propulsion wasn't science fiction, it was engineering reality. Milton Klein, the manager overseeing the program for the Atomic Energy Commission and NASA, became its political warrior, fighting budget cuts and public skepticism, arguing that NERVA represented America's best chance to maintain space superiority. The pieces were falling into place. The technology worked. The mission architecture was designed. The political will existed, at least among space advocates. Mars was within reach, not as a distant dream, but as a concrete goal with a concrete timeline. All the ingredients were there for humanity's greatest adventure, except one. Behind closed doors, other calculations were being made. Calculations about fallout patterns, atmospheric dispersion, and statistical casualties. Because while NERVA didn't require nuclear detonations, it wasn't clean. It couldn't be clean. The very physics that made it revolutionary also made it dangerous. The problem was inherent to the design. A NERVA engine worked by pumping liquid hydrogen through a nuclear reactor core heated to extreme temperatures. The superheated hydrogen would then be expelled through a nozzle, generating thrust. But inside that reactor core, neutrons were flying everywhere, and some of those neutrons would inevitably strike hydrogen atoms, transmuting them into radioactive isotopes. Not much, just a tiny fraction of the total propellant. But when you're expelling tons of hydrogen per second, even a tiny fraction adds up. And that radioactive hydrogen wouldn't just disappear, it would be expelled into the upper atmosphere where it would gradually spread across the entire planet, eventually settling back to Earth's surface. Everywhere, diluted, dispersed, but present and radioactive. The health physicists did the calculations. They modeled the dispersion patterns. They estimated the dose rates, and they arrived at a number that would haunt the program. Each NERVA-powered launch would kill between 0.1 and 1 person worldwide from radioactive fallout. Not immediately, not visibly, just a statistical increase in cancer rates across the global population, an invisible toll paid in incremental risk spread across billions of people. One launch might cause one additional cancer death somewhere on Earth. Maybe in Tokyo, maybe in Paris, maybe in a small village in Kenya. The victim would never know. The engineers would never know. It would be completely untraceable, lost in the statistical noise of background cancer rates. This was the moral paradox at the heart of NERVA. The deaths were real but abstract, certain but unidentifiable. It was a trolley problem at cosmic scale. Do you pull the lever to divert the train toward Mars, knowing that doing so will definitely kill someone, even though you'll never know who? The engineers tried to rationalize it. NASA had lost 3 astronauts in the Apollo 1 fire, and the program continued. Test pilots died regularly pushing the boundaries of aviation. Wasn't this just another acceptable risk in the name of progress? Besides, the United States and Soviet Union had already conducted hundreds of atmospheric nuclear tests during the 1950s and early 1960s, each releasing far more radiation than a NERVA launch would the planet was already contaminated. What was one more rocket? But there was a difference, and everyone knew it. Nuclear weapons tests were justified, however tenuously, by national security, by the existential threat of the Cold War. They were presented as necessary evils to prevent something worse. NERVA was different. NERVA was optional. It was about Mars, about exploration, about ambition. And while those goals were noble, were they worth killing for? Could you look at a map of Earth, at the billions of people going about their lives, and say, one of you will die so we can go to Mars faster, and I think that's acceptable? The engineers who had to make these calculations weren't monsters. They were people trying to honestly assess risk, to weigh costs against benefits, to make rational decisions about irrational questions. Some argued that the risk was negligible compared to other hazards humanity routinely accepted: car accidents, industrial pollution, natural disasters. Others felt a creeping horror at what they were contemplating. How do you tell your colleagues that their life's work, the project they've dedicated years to perfecting, will inevitably kill someone? How do you continue working when you know that? The debates happened in conference rooms and internal memos, hidden from public view, because the public conversation was still about Mars, about American supremacy, about the glorious future of space exploration. But privately, the moral foundation was crumbling. The very thing that made NERVA revolutionary, its nuclear power, made it ethically untenable. You couldn't have one without the other. There was no engineering solution to a moral problem, and the context was shifting. NERVA existed within the larger framework of the Cold War nuclear arms race, and by the early 1970s, that framework was changing. The Partial Test Ban Treaty of 1963 had already pushed nuclear testing underground, reflecting growing international consensus that atmospheric nuclear operations were unacceptable. Détente was replacing confrontation. Arms control was becoming politically popular. The Apollo program's success had paradoxically undermined NERVA's case. America had already won the space race using chemical rockets, so why risk nuclear ones? There was also the dual-use problem. The same technology that powered NERVA could be weaponized. a nuclear thermal rocket engine could, with modifications, become a weapon delivery system. If America deployed NERVA, the Soviets would feel compelled to develop their own nuclear propulsion program, escalating the arms race into space. Every advance in space nuclear technology was an advance in weapons technology. The dream of peaceful nuclear propulsion was naive. You couldn't separate the rocket from the reactor, and you couldn't separate the reactor from the bomb. By 1972, NERVA had survived every technical challenge. The engines worked. The tests succeeded. The engineering problems were solved. But the program couldn't survive politics, public opinion, and the growing realization that some technologies are too dangerous to deploy, no matter how well they work. In January 1973, President Nixon's budget eliminated all funding for NERVA. The official reason was budget cuts in the post-Apollo era. Space exploration was expensive, public interest was waning, and there were pressing problems on Earth that needed attention. The unofficial reasons were more complex: environmental concerns, proliferation fears, shifting political priorities, and the uncomfortable moral calculus that no one wanted to defend publicly. The cancellation was swift and final. Test facilities were mothballed, teams were disbanded, decades of research were archived. The institutional knowledge that had been so carefully built, the engineers who knew how to safely operate nuclear reactors and rocket engines, the technicians who understood the systems, the managers who could navigate the bureaucracy, all of it scattered. Harold Finger and Milton Klein, the program's champions, watched their life's work disappear. One can only imagine their feelings. Disappointment, certainly. Frustration at what might have been. But perhaps also relief? The moral burden lifted? We'll never know. The speculative alternate timeline is tantalizing and terrifying in equal measure. If NERVA had continued, we might have had permanent Mars bases by the 1990s. The solar system might be humanity's backyard, with routine flights to the outer planets, asteroid mining operations, perhaps even interstellar probes. We would be a different species, defined not by our confinement to one planet, but by our expansion across the cosmos. The technical capabilities NERVA represented would have opened doors that remain closed today. But we'd also have normalized atmospheric nuclear operations. Each launch would have added to the planet's radioactive burden. Accidents would have been inevitable. A launch failure scattering reactor material across populated areas, a malfunction during orbital insertion, a collision in space spreading nuclear debris. The cumulative cancer toll would have mounted silently, invisibly, a price paid by people who never consented and never benefited. We might have Mars, but we'd also have a more contaminated Earth. We might have reached the stars, but at the cost of poisoning our home. The story of NERVA isn't just about what we lost. It's about what we learned, and what we're still struggling with today. We learned that technical possibility doesn't equal moral imperative. We learned that the most important engineering challenge isn't building more powerful engines, but building wisdom to match our capabilities. We learned that sometimes the most courageous decision isn't to push forward, but to step back. Today, as we stand on the edge of a new space age with commercial spaceflight, renewed lunar ambitions, and Mars missions on the horizon, NERVA's ghost haunts us. NASA is researching nuclear thermal propulsion again, but with modern safety standards, different reactor designs, and decades of additional knowledge about radiation effects. The dream hasn't died, it's evolved. We still want Mars, but we want to get there without statistical death sentences and radioactive exhaust. The question isn't whether we'll use nuclear propulsion, but when and how we'll do it responsibly. The engineers who built NERVA weren't villains. They were visionaries who pushed boundaries, asked uncomfortable questions, and ultimately helped us understand where those boundaries should be. They gave us a gift, though perhaps not the one they intended. They showed us that we're capable of building almost anything we can imagine. But they also showed us that capability alone isn't enough. We need wisdom, restraint, and the courage to say no to our own ambitions when the cost is too high. In a bunker in Nevada, there's probably still equipment from those tests in 1968, too radioactive to move, slowly decaying over decades and centuries. It's a monument to what we almost became, a species willing to poison our own planet in pursuit of others. The fact that we chose differently, that we canceled NERVA despite its technical success, might be one of humanity's finest moments. Not because we gave up on Mars, but because we refused to get there by leaving bodies in our wake. We're still going to Mars. We're still going to the stars. But we're going to do it right, or not at all. That's the real legacy of NERVA. Not the rocket we built, but the rocket we chose not to fly. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.